In this video, I'm going to show you how to create a central composite design in Python, like the one that I have here. I'm going to assume that you already know what a central composite design is and when to use it. If not, then go and watch the video that I have linked in the description first. Otherwise, let's get started. We are going to use the PyDOE package to create the design. I find it quite good and intuitive. The most recent version is PyDOE 3. So let's start by installing that real quick. When you run this command, you'll see it downloading and installing the package. If you already have it installed, it might tell you that the requirement is already satisfied, like I have here. After the installation, we can import it into our Python environment, and we specifically need the CC design function from the PyDOE package to create central composite designs. We also import pandas and numpy as we need those later to make everything look pretty so that we can work more easily with the data. The general syntax for creating a central composite design is really straightforward. You just call the CC design function, and in here you can specify n, which is the number of factors. You can specify center, which is the number of center points as a tuple. Then we can specify alpha, which is the distance of axle points from the center. And then we have the face parameter, which is the orientation of the design, but more on that a little bit later. For now, let's just start with a very simple central composite design for just 2 factors. And for that, we only call the CC design function here and specify the number of factors, which in our case would be 2. And the output is a coded design matrix where each row represents an experimental run that you'll need to conduct. We have the 4 factorial points here, then the 4 axle points that extend outside the design space, and in this case we have a total of 8 center points, 4 for the factorial portion of the design and 4 for the star points. Now, if you do not want or not need so many center points, you can customize that by adjusting the center parameter. And the center parameter, it's a tuple where the first number represents the center points for the factorial portion of the design and the second number represents the center points for the axial portion. My guess for why you can or why you have to define separate center points for the factorial and the axial portion of the design is that often you come from a factorial design and often you already have executed center points in that factorial design. So by defining them separately, you can account for that. The more variability you expect from your experiment, the more center points you should include. And if we execute this code, you'll notice how the number of center point has changed from previously 8 to now only 4. Now, the face parameter is another important parameter to customize. The default here is circumscribed, which means that the axle points extend outside the factorial square. But sometimes that is not possible. For example, if the factor that you're testing is the concentration from 0 to 1%, then you can of course not extend outside the design space and test a negative concentration. In that case, you can change the face parameter to inscribed or phased. For inscribed, the factorial points are scaled down so all points fit within the range you're testing and the axial points do not extend outside the design space anymore. So the axial points are now at 0 and +1 and the factorial points are at 0.7 somewhere. Now for phased, the factorial points are left untouched and only the axial points are scaled down and put on the faces of the factorial space. The benefit here is that when you come from a factorial design, you do not have to discard the experiments you already performed, but can still use them. That's not the case if you go for an inscribed design. But the drawback is that a phased design is not rotatable anymore. Rotatable designs ensure a uniform prediction error throughout the design space, and that is not the case anymore when you go for a phased design. Now, the last parameter that we have control over is the alpha parameter. It defines how the distance of the star point from the center is calculated. I would default to rotatable, and I don't think it's very important in practice, but correct me if I'm wrong. Okay, Now let's create a central composite design that is actually user-friendly and that you can take to the lab. And to do that, we start by creating the design with the CC design function as we did earlier. I'm going to have two factors, temperature and pressure. I also want a total of 4 center points. I'm going to use a rotatable design and I will set the phase parameter to CCC. So this is a circumscribed design with the axle points extending outside of the design space. And now we can convert this design matrix, this array, to a data frame and give meaningful column names. And this is how the result looks like, which is already much better, but we also want to define the actual temperature and pressure ranges. And I created this function here to do that. It will take the design from earlier as input together with the actual factor ranges for our factors. So to use the function, I need my design matrix from earlier, define the factor ranges as a tuple the way I did here, and then we're good to go. And this is what the result will look like, that we can also save as an Excel to record the results. The scaling function is going to work for any number of factors and any design phase. Try it yourself, the link to the code is in the video description.